Hello, good morning, everybody. Welcome on the next webinar. Today we will be discussing the last VNR update, version 6.2. And in this version, we've prepared for you many new resources, and also we made a couple of changes and a few improvements for the VNR. So the same like for the previous webinars. For the first thing which we will be discussing are new resources. So in this webinar, in this version, we prepared many new XOR keys for you. As you can see, this portion is quite big. Few silicon motion XOR keys, a couple of Phison XOR keys, XOR keys for FC controllers. Also, except XOR keys, we have a new ACC and BCH files for the correction, and of course, new configuration for NAND memories. Also, as you can see, you probably noticed that previously on the website, in this release, in new releases, in new upcoming VNR updates, you will be able to notice this kind of configurations more often. So configurations which will allow you to read NAND memories in SLC mode. Some of the controllers, especially like this new devices, new SD cards, for example, with high endurance, they are usually writing data in SLC mode. And using this configuration, you can read the dump from such a device which was using SLC mode, and you will be able to extract data later on. So configurations which inside their names they include this phrase SLC. It means basically that this configuration is prepared for reading the dump in SLC mode. Like I said, some of the controllers they may only read and write data to NAND memory, particularly using this exact mode. So now you will see this configurations more often, and that would be everything for new resources. Next thing, of course, we have a new Pinouts. In this update, we have two unstandard TCP48 chips. You have a pinout for this ones in the database. You can already check them. We have two micro SD cards, two new pinouts for micro SD cards, and one pinout for UFD device. So in total, we will have 5 new pinouts. And next, of course, we made, as usual, we made improvements. We fixed some issues inside the VNR, and this minor improvements will be following. So first of all, we increased speed of AI-XOR elements. So basically now, in case you will be using silicon motion XOR key, which uses XOR synthesis. This synthesis will be now significantly faster. And for all these elements which are using this XOR synthesis, this speed have been increased. Next thing is file assembler, and here we fixed slightly internal algorithm. In some of the cases, a basic scan was taking a little bit longer time. So now in this version, you won't have any problems with basic scan. It's now it works faster. And for the fixes, we fixed one internal issue in pair element. We fixed problem with CBM XOR, and now you have a possibility. We've added additional read ID mode for Samsung chips which are using 16 bits. These chips, they doesn't have standard pinout, and sometimes if you will previously, in case you will press this read memory chips button, VNR is testing multiple configurations. So it tests the voltage and so on. In this case, in this update, we added yet another mode. And this mode is prepared particularly for this Samsung chips, which are using 16 bits. Previously, you won't be able to read ID using normal mode ONFI configuration. Now basically this VNR basically will allow you to will tell you that this chip is using Samsung Pinout and 16 bits. And of course, except that many minor bugs have been fixed. And in overall, now basically VNR has a less amount of bugs. And now we come to the significant changes. And first thing is Retry database. We move this database now to cloud. Now basically each time you will launch VNR, your database will be synchronized with your Retry database will be synchronized with the one which is located on the cloud, which resides on the cloud. So basically, in case we will change something, in case we will release some new Retry, we will change some sets of commands for some particular Retry. Automatically, you will get this change. Your database will be automatically updated, and you will get the most recent version of this database. So this is the small change. Of course, here in this menu, you have also this. It was slightly changed because previously you didn't have this drop-down menu. Now you have this drop-down menu. You can select with the Retry which you want to test. However, please keep in mind that in case NAND ID is supported, this Retry file will appear automatically. In case this menu is empty, it means that this memory wasn't tested, or Retry for this memory for now is not supported. So it looks like in case of this menu, this is the only change. You have this drop-down menu and synchronization with the cloud database. And the next thing, the next element which we changed is we significantly changed interface for bad column remover. Now basically we've implemented to bad column remover auto detection. So now basically all these bad columns are being located and filtered automatically. Everything happens basically in the background. So now you don't have to care about all these filters. You don't need to worry about false positive and stuff like that. All these filtrations, all this filtration is being done in the background. So now basically you need to click. You are basically limited to a couple of buttons, and after that you will get all possible bad columns inside a particular plane. And the next thing, so now basically all this detection but position of bad columns are being detected automatically. They are being filtered automatically, and also we added one feature, which is multi-plane auto detection and single plane auto detection. Some of the controllers which are using multi-plane page allocation, due to multi-plane page allocation, we can always constantly see data in physical blocks from in neighbor physical blocks, which belongs to the different planes. So this multi-plane page allocation we have almost always in case of FISO, in case of SanDisk controllers, in case of Silicon Motion controllers. So now basically, in case you have, for example, two bad columns, so you have two planes, this this bad column removal will be automatically done for each of this plane. So we don't have to switch it manually. Everything will be done automatically. In case of other controllers, in case of Alcor Micro, ChipsBank controllers, and some other controllers, they may use single plane page allocation mode in majority of the cases. And in this case, you have here a single plane auto detection, which means that you have to run auto detection yourself for each plane. So you have to switch it manually. And of course, this type of auto detection is banded with the preset which you will select. Okay, so now let's speak about the procedure, how it looks like. It has been significantly simplified, in my opinion. Now, basically, like I said, you are limited to 3, depending on a case, maybe 4 buttons. And first thing, the same like for previous element, at the first point, in the first step, it's necessary to find the block with data. Find and select the block with data with left mouse button, and then you will have to select preset based on the controller which you have. Next, you will have to run auto detection and click add all bad columns, and actually it will be everything. So using these 3 buttons, in case depending on the case, you will be able to detect all these bad columns automatically. Like I said, in case of Alcor Micro preset, ChipsBank preset, and Universal preset as well, you'll have to also repeat this procedure for the other planes because this controller doesn't use multi-plane page allocation mode. It's necessary to switch this plane manually and repeat these three steps. So preset, auto detection, and bad columns, and then you can switch. You can close BCR and you can check if all these bad columns have been removed properly, and you can proceed with the next elements. For this webinar, we prepared 2 practical cases. So now we will go through these cases, and you will see how this new bad column remover work in practice. Let's open the first case. So on the first example, we have a silicon motion controller, and as you probably know that in most of these controllers, these bad columns are clearly visible through the bitmap viewer, and usually, in case you will want to remove them, manually, you wouldn't have the problem here. However, in case these bad columns, you'll have like 100 bad columns, it will clearly take a bit of time. So this bad column remover is basically made to save your time, which you have to spend for recovery. So these bad columns will be visible in case of silicon motion controllers, and we also have the next case, which is Alcor Micro XORed columns, and here situation is completely different because in this case, in case of these controllers, these bad columns are not visible on the bitmap. In case you will have such case for the first time, you won't be able to see. You wouldn't be able to see any possible positions where these bad columns are located. Why it happens? It happens because pattern of bad columns here in case of Alcor microcontrollers depends on the previous data. Depends on the previous user data which was recorded to NAND memory. So basically, what this controller does, this controller is replicating. This controller replicates byte for user data onto bad column position. So in case we have on some particular position we have a bad column, the former byte from the buffer will be written onto this bad column. So you won't have here a pattern like FF or some zeros. You'll have the pattern of the previous byte of data. Like you can see on this example as well, we have 3 times this column was repeated 3 times, and one of these columns will be user data, and two repeated columns will be our bad column, and it will be necessary to filter out these columns. So now basically this filtration previously this algorithm for Alcor Micro controllers for this particular preset was basically we completely changed approach here. I mean, in the background, of course. So previously, this algorithm was based on comparison. So basically, we were reading bit statistics of each bit column, and then we were comparing them. Because as you can see, they are similar. They are similar visually, and their bit statistics were also similar. So we were comparing them. However, in cases where we had a lot of bit errors, in cases where we have a lot of bit errors, we were getting sometimes not all of these bad columns were found. It was necessary to repeat procedure for procedure of detection on 5 blocks, maybe 10 blocks, depending on the case, depending how many bit errors was inside. Now this approach, like I said, was completely changed, and it doesn't matter actually how many bit errors you will have inside particular block which you are testing. All of this basically, all of these columns will be anyway detected because we have here the new approach. So let's take a look on the first case. Let's take a look on the first case, and here we will have a circle motion controller. Okay, so we have a physical image from this this controller, and now let's take a look on the physical image. So regarding that, we have a circle motion controller. Of course, to check the first thing which you will do in order to check whether these bad columns are present inside the dump, you will have to go to the end of the page, and we have to take a look on service area. I also always recommend you to use this highlight box function. If you will press it, you will have highlighted physical blocks. So one block will be from one plane, next block will be from the next plane, and so on. And if you will go through a few of these blocks, you will be able to see that we have some shifts. We have some shifts. So now two physical blocks, their position is synchronized, and now we have to take a look on some bad column to determine the amount of planes. So on this position we have a bad column. Okay. Okay, so as you can see, in this case, we have 4 planes, because by looking on this bad column position, we can see that these bad columns are located on different positions in 4 of these physical blocks, which means that in this case we have 4 planes, and now it will be necessary to remove this bad columns, and we will need to grab bad column remover element. We have to configure number of planes to 4 planes. All this settings for structures will be automatically proper, because this physical image element contain the same sizes like configuration has, and for each configuration which you can find in our database here, all these configurations are basically configured to physical blocks. So this block, which will be located on the physical image, it will contain a physical block size, and this physical block size will be automatically placed here in BCR configure in BCR parameters. So now we have to click edit, and first thing is we have to select preset. So in this case, we will go for silicon motion preset. Now we have to run auto detection. Run auto detection and add all bad columns. So now, as you can see, positions of bad columns from the first plane have been found, and also if we will go through the different planes, these bad columns will be located here as well. So now, because we have a silicon motion preset, this procedure will be repeated for each of this plane automatically. Previously, you probably remember how this filtration was looking like in this element. So basically, based on the controller, based on the preset, it was necessary to click on this indexes here, right mouse button, and select proper presets, proper filters. Now all of these things have been removed. You don't have this filters anymore. You don't need to worry about that. Everything is happening. Everything is done automatically in the background. After you will press auto detection, all these bad columns will be found, and they will be filtered automatically. So no more filtration, no more this manual filtration from this menu here. Everything is done by auto detection. Okay, so now we remove bad columns, and to check this out, we can grab ECC, and let's take a look if we'll be able to find the file. Okay, so this is our file. We can take structure from ECC also, and in case you want to check whether these bad columns were removed properly or not, we can also take a look on ECC map. I will slightly expand this. And on ECC map, you have this white line. This white line basically separates blocks. So it's basically separator. We have a physical block here predefined in our ECC, and this line separates physical blocks from each other. So physical blocks which belongs to each plane. So we have a physical block from the first plane, second plane, third, and fourth. And as we can see, all of these bit errors can be fixed. In case there will be some bad columns, there will be some like not selected bad columns. You won't be able to either find this ECC file, or in ECC map, you will be able to see that all these boxes for particular physical block from particular plane will be not correctable. In this case, it means that there are still some bad columns inside. Of course, same situation you will be able to see on BCR element, and you can take a look on the service area. In case service areas will be shifted, the same thing. It means basically that these bad columns will be, there are some bad columns left inside the dump, and it will be necessary to repeat this procedure. But in most of the cases, you won't have to do this. Everything will be done automatically. Okay, so this was the first case. Silicon motion. This example basically, this procedure will be looking similar for the other controllers, like files on SanDisk and so on, because these bad columns will be visible. These bad columns, we can see them basically on the bitmap. A different situation takes place in case of Alcor Micro. We'll open the next case. A different situation take place in case of Alcor Micro controllers, because these bad columns won't be visible. Okay, so here we have a physical image from Alcor microcontroller. We can open it. We need to find some block of data. Let's go highlight blocks. And now the same thing, which we did in case of silicon motion controller, we can try to find the service area, and we can compare their positions. So we have a physical block from one plane and physical block from the next plane. As you can see, these blocks have different patterns. In the first block, we have a noise pattern, and in the next one, we have a XOR pattern. It means that in this case, we have two planes, because this pattern of data is different. Let's go till the end. And as we can see, at the end of the page, in the last code word, this service area are shifted. It means basically that we have bad columns inside, and it will be necessary to remove them. And in case of Alcor microcontrollers, which are using, we are calling this bad columns XORed bad columns, you won't be able to notice this bad columns through bitmap. In case you will scroll here horizontally, maybe you will find some distortions. However, for the first time, in case you have such case, you won't be able to see actually any differences. So to determine whether we have these bad columns or not, we can also check the service area. And in case we have XORed bad columns, you won't be able to see any patterns characteristic for bad columns, like in case of silicon motion, Phison controllers. These columns won't have any static pattern like FF or zeros. Here, this pattern will depend on the previous bytes of user data, which was recorded to this NAND memory. Okay, so we can see that we have a shifted service area, and now we will need to switch to bad column remover. Let's click bad column remover. We have two planes. We've seen different patterns in neighbor blocks, which means that we have two planes. Physical block size, like I said, it will be automatically here. Page size also, we don't have to configure anything here. Just make sure amount of planes is correct, and then we can click edit. And the first, of course, the first thing which we'll have to do is to select preset. Now, as we can see, this first block, this is actually a SLC block. Such blocks should be skipped, because also the same like for similarly to the previous version of this BCR, we are still operating on bit statistics. For some of the presets, like for Alcor Micro, this algorithm in the background was slightly changed, but still it's based on bit statistics. So we will have to find a proper block which we can analyze, and the block which we are looking for is the block with user data. So the block which has a noise pattern, we have to select such block. With leftmost button, you need to have located this marker on this block. Number of currently selected block is also over here, in case you didn't know. And yeah, so we have a block with data, we have an Alcor Micro preset, and now we have to run auto detection and add all bad columns. And now these bad columns will be automatically transferred to this menu. And the Alcor microcontrollers, they doesn't use, in most of the cases, in 90% of the cases, this controllers doesn't use multi-plane page allocation mode, which means that in physical block from one plane, we may have data, but in the same physical block from the next plane, we won't have this data. So sometimes you will see that one time you will see that, like for example here, we have a block of data. In case we will switch the planes, you'll be able to see that this block doesn't contain user data. It's in this case, it's most likely bad block, and because this controller doesn't use multi-plane page allocation, patterns of physical blocks may be different. So we disabled this multi-plane mode for this presets exactly from this reason, because of this multi-plane page allocation. So these patterns may be different. And as you can see, such blocks which doesn't contain user data couldn't be analyzed. Otherwise, we will get many false positives. So for the first plane, we have to run auto detection, select these columns, and repeat this procedure for the plane number 2. Here, we also need to find the proper block which we have to test. And you probably remember that in case of, for the old version of bad column remover and the Alcor Micro preset, we have to avoid block with XOR keys. So such blocks, basically, we're supposed to find block with data with noise pattern. Blocks which contain XOR key, like this one, for example, should be skipped. And this particular case, as we can see, many of these blocks from the second plane, many of these physical blocks have only this exact pattern. It may be a little bit hard to find block with user data. You'll have to go through all of these blocks, look for noise pattern. You don't have to do this now. It doesn't matter. We change this approach, and now basically, no matter which block you will select, these bad columns will be detected. So either block with XOR or block with data. SLC blocks, bad blocks, blocks with some pattern which isn't characteristic for XOR or user data should be skipped. Normally, we have some examples here. So, for example, such blocks, of course, these blocks, blocks with this pattern should be skipped. We're supposed to select block with data, so either with XOR or user data. And of course, we have to run auto detection, select this block, run auto detection, and for the second plane, add all bad columns. And now this removal will be done. So that's how this procedure looks like. Previously, we also, this filtration was being done. You have to click on this index here, right mouse button, and go through all of these steps. It was basically a semi-automatic mode, in fact, a semi-automatic bad column remover. But anyway, it was taking a little bit of time to go through all of this. Then it was necessary to check if all of these bad columns were selected. Now you don't have to worry about that, really. No matter how many bit errors we have, no matter which block with data, what kind of data is inside, what kind of data was recorded in memory, you don't need to care about this anymore. You just need to find this, select the block, run auto detection, and add this bad columns, mark bad columns, this particular bytes as a bad columns, and it would be everything. Okay, so now we have patterns of these columns. This is a bad column which was found, and it looks like this more or less. So basically, we have, in case this controller encounter bad column, former byte from the buffer is being written onto this position where we have a bad column, and you see exactly same patterns. So visually, it would be really hard to notice that okay, this particular byte, on this particular byte we have a bad column. It won't be exactly possible. I mean, after some period of time, after we get many of these controllers with this exact feature, you'll be able to most likely find them visually through the bitmap. But like I said, it's not required. You have this bad column remover. It will be these things will be done automatically for you. So one of these columns, the first one, as we can see, maybe I will mark you this box over here, so it will be more visible for you. Let's focus on this area. So we have this sort of pattern, and this pattern, exactly same pattern, is being repeated three times. So one byte, the first column will be our column where we have user data, the column which we supposed to keep the column which we supposed to include to our case, and the two columns with exactly same pattern, two repeated columns. And these two columns will be a bad column, and it will be necessary to this two, it will be necessary to remove. So that's how it looks in case of XOR. In case of data, take a look. It looks like this. So it's quite hard to spot such. It will be visually, it will be really hard to spot such bad column. And of course, like verification stuff may be really hard also. So now basically all these columns will be detected automatically, and in fact you don't have to really check this results. Sometimes in some of the cases, let's assume some worse situation that you have a yes, of course, these bad columns also can be done, can be selected manually, of course, with Shift and left mouse button, and you can uncheck them with Control and left mouse button. So this bad column remover also have this features, this particular feature from the previous one. So this is still available. Okay, so this bad columns will be selected automatically. Visually, this columns will be really hard to find. Okay, so sometimes in some, like I said, in some exceptional cases, let's assume that we will have the worst situation. We have a significant amount of bit errors, some really bad case, or maybe some really bad block. Sometimes you may have to run this auto detection on 2 blocks in case you don't have all of these columns, in case not all of these columns have been detected. But in fact, like I said, in 90% of the situations, you won't have to do that. To do that, 1 block will be usually enough to find all of these bad columns, even if it has bit errors inside. So now we marked all of these columns, and now let's take a look if all of them were removed. If all of these columns have been removed properly, let's try to find the ECC file, and once again we will take a look on the map. Okay, so we can grab ECC file and let's open the map. Let's find some block with the data. The first block on the very beginning, of the dump. Almost always you have SOC blocks, and this type of blocks won't have a proper ECC map. And this is our block with user data. You can see blocks from 2 planes, physical blocks from 2 planes. And as you can see, we have correctable errors, which means that all of these bad columns were removed correctly. We can also take a look on the positions of service area. And let's see if these service areas are synchronized between the planes. So let's take a look. And as you can see, every time we have the service areas are on the same position. To speed up the process, you can only take a look on the last service area. In case the service areas are synchronized, it means that all of these columns were removed properly, and then you can proceed with next steps. So XOR key, markers table, and so on. So that would be everything for this webinar. Thank you very much for the questions, and we will see you on the next webinar.